Alright, in this video we will cover the notes for section 3.6 on Cauchy-Euler's equation. So in this section we will solve higher order linear differential equations where the coefficients are variable. So unlike the equations we solved in the previous couple of sections where the coefficients were only constants, so the general second order differential equation with variable coefficients, which has this form, that is ax squared y double prime plus bx y prime plus c y equals to 0. So unlike the exponential solution we proposed in the previous type of equation, our solution would be of the form y equals x to the m, that is x to a power m, where, well, we will take the first derivative y prime, that is mx to the m minus 1, and the second derivative, which is y double prime m times m minus 1 x to the m minus 2. So let's substitute these derivatives into the differential equation, that is ax squared y double prime, which is m times m minus 1 x to the m minus 2, plus bx times the first derivative, which is mx to the m minus 1, plus c times y, which is x to the m. Let that be equal to 0. Alright, well, how do we simplify or solve this equation? Well, because we have constant coefficients, some x's, some m's, and, well, there's a lot going on right here. Well, so number one, I'm going to use the law of exponent a to the m, well, rather x to the a plus b, which is x to the a times x to the b, to rewrite this x to the m minus 2 and x minus 1 factors, so we can simplify some factors there. Well, that is ax squared m times m minus 1 x to the m times x minus 2, x to the negative 2 rather, plus bx times m x to the m times x to the negative 1 plus cx to the m power. Let that be equal to 0. Okay, so how is this helpful? Well, that's to cancel out x squared with x to the negative 2 and x with x to the negative 1, which are inverse multipliers, if we will. All right. Okay, so that's going to leave us with the quantity a m times m minus 1 x to the m plus b m times x to the m plus c x to the m. Let that be equal to 0. Well, notice in this equation we were left with x to the m is the greatest common factor, so I'm going to factor out x to the m, and that's going to leave us with am times m minus 1 plus bm plus c, and let that again be equal to 0. And then x to the m times, I'm going to distribute a to the m to m times m and negative 1, so am times m minus 1 plus bm, oh wait, I was supposed to distribute it, so that is am squared minus am plus bm plus c. This is equal to 0. Alright, well, there's really no terms to combine. However, notice how the second and the third term right here, they have a common factor as an m. Let me factor it out so you can see the result we're going to get. Okay, so that'll be am squared plus, I'm going to write the positive first, which is b minus the negative, and then b minus a times m plus c equals to 0. All right, and well, okay, so that's actually using the zero product property. On the one hand, either x to the m equals to 0, which would be the solution y equals to 0, because, y equals x to the m. But wait, I mean, the solution y equal to 0, it's not very relevant, it's not very interesting, because of course the derivative of 0 is 0, the second derivative of 0 is also 0, so of course this is going to check the differential equation. So we will instead use the polynomial am squared plus b minus a m plus c, and let that be equal to 0. All right, so that is going to be our characteristic equation or auxiliary equation. Well, so just like the differential equations with constant coefficients, our for the Cauchy-Euler's equation, we'll have three different cases. If the solutions to this quadratic equation are real and distinct, that the solution type will look like y equals c1 x to the m plus c2 x to the m1 and m2. All right. And for case number 2, when the two solutions m1 and m2 are real but repeated, well, it's going to look c1 x to the m1 plus c2 x to the m1 also, but in this case multiplied by a power of ln of x. If this were a cubic repeated, it would be plus some c3 x to the m1 ln of x quantity squared, and then we would be multiplying by powers of ln for even higher order. And for the case where m1 and m2 are complex, well, that's going to be the solution is going to be of the form y equals x to the alpha, which is the real part of the complex number in the solution to the polynomial, times c1 cosine of beta ln x plus c2 sine beta ln x, where beta is the imaginary part of the solution. All right, well, let's solve each differential equation below right here to see this in action. Well, so solving the equation x squared y double prime plus xy prime minus 9, y equals to 0. So we propose a solution to the equation of the form a m squared plus b minus a m minus 9. Well, in this case, it would be, well, wait, give me a second. Let me actually write it in generic form. am squared plus b minus a m plus c in this case. Let that be equal to 0. It would be worth to write down the constants, the coefficients. A equals to 1. There is an invisible 1. B equals to another invisible 1. And c equals to negative 9. All right, well, so let's solve this equation. That'll be a, which is 1m squared, plus b, which is 1 minus a, which is also 1m, plus c, which is actually negative 9, equal to 0. So this will be m squared, 1 minus 1, that's 0, so that term goes away to 0, and plus negative 9, that is minus 9, and let that be equal to 0. Actually, we can solve this quadratic equation using the the square root property. That is m equals plus or minus the square root of 9, which is plus or minus 3. So m1 equals to 3, and m2 equals to negative 3, or m1 negative 3 and then m2 equals positive 3. It doesn't matter. In the end, again, it's a superposition of solutions, and we are adding these terms, so it doesn't matter which one that you write first. Okay, so y equals to c1 x to the third power plus c2 times x to the negative 3 power. Final answer. All right. So, well, example letter B, 2x squared y double prime minus xy prime minus 2y. Well, here in this case, how about let's list a equals to 1, b equals to negative 1, and c, which equals negative 2. Okay, so again, let's write our generic equation, a m squared plus b minus a m plus c, and let that be equal to 0. So m squared, which is because a equals 1, plus b minus a, which in this case is, to be careful, b, which is a negative 1, minus a, which is 1, times m, plus c, which is actually negative 2. Let that be equal to 0. All right. Oh, wait. In this case, a equals to 2. Okay, let me take this back. A equals to 2. So, not 1. All right. So, that'll be 2m squared minus 2m minus 2 equal to 0. And well, in this case, we would need to factor a quadratic polynomial where the leading coefficient is different than 1. We have discussed many methods in lecture how to factor this polynomial. Use the one you feel more comfortable with. I'm just going to give you the result to this factoring, that is 2m plus 1 times m minus 2. All right. From here, this tells us m equals to negative 1/2, and this factor rather tells us m equals to positive 2. So we're good to go and write the general solution to the Cauchy-Euler's equation, that is y equals to c1 x to the negative 1/2 plus c2 x to the second power. And guys, you don't have to write this to the denominator with radical form. If you want, that's fine, but it's not necessary. We can leave it like this. All right. Let's do another one. Letter C. X squared y double prime plus 3x y prime and plus y equals to 0. Number one, let's list our constants. A equals to 1. This time I'm going to do it right. B equals to 3 and C equals to 1. Okay. So now let's write again the auxiliary equation, am squared plus b minus a m plus c, and let it be equal to 0. All right, so substituting, that is 1 times m squared, which is m squared, plus b, which is 3 minus a, which is 1 times m, plus c, which is 1. And let that be equal to 0. Okay, well, so simplifying this equation, that's going to give us m squared plus 2m plus 1. And let that be equal to 0. Okay, so solving this quadratic equation for m, actually by factoring, that's m times m. Okay, so that'll be factors of 1 that add up to 2. That's plus 1 and plus 1. Well, in this case, what do we have? M equals negative 1 as a repeated solution, unlike the other two cases where the two other solutions were real and distinct. In this case, we have repeated solutions, so that's going to be of the form y equals c1 x to the m1 plus c2 x to the m1 times ln of x times 1 factor of ln of x. All right, well, so y equals to c1 x to the negative 1 plus c2 x to the negative 1 ln of x. Final answer. All right. Okay, so let's do one more example, letter D. So for letter D, and we have the equation x squared y double prime minus 5x y prime plus 13y equals to 0. And again, in a similar way, the drill is the same. Let's list the constants, the constant coefficients first. That is a equals to 1, b equals to negative 5, and c equals to 13. Okay, well, so solving again, or substituting the coefficients into the auxiliary equation, that is a m squared plus b minus a m plus c equals to 0, where a equals to 1 times m squared, that's simply m squared, plus b minus a, which is negative 5, minus a, which is 1, plus, or times m, plus c, which is 13. Let that be equal to 0. So simplifying this, m squared minus 6x, no, not x, takes m plus 13. Let that be equal to 0. And well, let's look at this quadratic equation. So the first thing we try is whether the equation it's solvable by factoring. Well, so are there any factors of 13 that add up to negative 6? I'm afraid not. 13 is prime. The only factors are 1 and 13, and no combinations of addition of those factors add up to either positive 6 or negative 6. So guess what? Quadratic formula. So I'm not going to write the quadratic formula here because we typically write it in terms of a, b, and c. And I already use a, b, and c for the coefficients of the differential equation. So if I write the quadratic equation in terms of this a, b, and c, we may get confused and use these values which are not the same. So I'm just going to go m equals minus b, which is negative 6 from the quadratic equation, plus or minus the square root of negative 6 squared minus 4 times a, which is 1, times c, which is 13, times, or rather divided by 2a, which is 2 times 1. Okay, so that'll be equal to m equals to minus minus equals to 6 plus or minus the square root of 36 minus 4 times 13, which is 52. And everything divided by 2, which reduces to 6 plus or minus the square root of 36 minus 52 is that negative 16, which is divided by 2, and m equals to 6 plus or minus the square root of negative 16, which is 4i. Everything divided by 2. And we'd better simplify this to the format alpha plus or minus beta I, that is 6 over 2. And even if the numbers don't go, don't divide out evenly, leave them as fractions. In this case, both 6 and 4 can be divided by 2 and get a nice number. So that is 3 plus or minus 4 over 2, which is 2i. This, so we can see that alpha equals to 3 and beta equals to 2. Again, beta does not include the imaginary unit. It only includes the coefficient of the imaginary unit, or the number that multiplies I, in other words. All right, well, so in this case, the solution would be, the general solution would be of the form y equals to x to the alpha c1 cosine of beta ln x plus c2 sine of beta ln x. All right, that is y equals to x to the alpha, which is x cubed, c1 cosine of beta, which is 2 ln x, plus c2 sine, also 2 ln x, right? Final answer. All right. Now, what do we have so far? In these few examples, these 4 examples, we had pretty much one example of every single case, except the second example. It's a case of repetition where the 2 solutions are real and distinct, except that I used a polynomial where the leading coefficient is different than 1. Now, what else can we do with Cauchy-Euler's equation? So in the next topic, I'm going to solve an example of a non-homogeneous Cauchy-Euler equation. So what do we do in this case? Well, we rely on the method of variation of parameters, which is the section we covered in the topic we covered in the previous section in lecture. Right? All right. So let's solve the following differential equation, that is x squared y double prime plus x y prime minus y equal to 4x ln x. Well, notice how the right hand side of the differential equation is no longer a 0. That is, it's no longer a homogeneous equation. So we're going to use we're going to use variation of parameters to solve this equation, because again, we're going to solve the related. So we're going to solve the related homogeneous differential equation, that is a, in this case, a equals to 1, b equals to 1, and c equals to -1. That is, these are the numerical coefficients of the of every single term. All right, so using the auxiliary equation, am squared plus b minus a times m plus c equals to 0. So let's solve the homogeneous case first, and then we would look at the superposition of the y homogeneous plus the y particular. All right. Okay. So that is 1, which is 1 times m squared. That is m squared plus b minus a, which is 1 minus 1 m plus c, which is -1. That be equal to 0. All right. So let's see. That's m squared, 1 minus 1, which is 0, m minus 1, let it be equal to 0. This is a quadratic equation that again we can solve using the square root property. M equals plus or minus the square root of 1, which is plus or minus 1. All right. So let's form the solution y sub c, that is the complementary or the homogeneous solution, that is yc equals c1 x to the first plus c2 x to the -1. All right. Okay. So from here, it would be worth to do the following. That is, well, let me rewrite simply yc equals to c1x, because x to the first is simply c1x, plus c2 x to the -1, where y1 equals to x and y2 equals to x to the -1. And the reason why, again, I'm listing explicitly what y1 and y2 are, that's so we can set up our Wronskian. That Wronskian we need to solve, or rather to find the particular solution in the variation of parameters. So that is y1, y2, and then the second row would be the derivatives of these two elementary solutions. Okay, so that is y1, y2, which is x and x to the -1, y1 prime, okay, the derivative of x, which is easy, that's 1. The derivative of x to the -1, be careful, that's -1, that's a negative, x to the -2. Now let's compute this 2 by 2 determinant, again, by multiplying the elements along the main diagonal, that is x times -x to the -2, minus the product of the elements along the secondary diagonal, that is -1 times x to the -1. Multiplying each of them, that is positive times a negative, that's negative x to the x times x to the -2, but this is an x to the invisible 1, at the exponent 1 plus -2, that's x to the -1, and minus x to the -1. And actually, these are like terms. So let's combine this to -2, x to the -1. I know what you might be thinking. Rewrite this -2 x to the -1 as with positive exponent, but actually when we set the equations for, or rather the integrals rather for u1 and u2, we would rather have this in with negative exponents. So u1 equals the integral of -y to g of x divided by the Wronskian with respect x. Now you need to be very, very careful with g of x, which is the forcing function in our equation. So you might recall that when we define these integrals to find the particular solution for the for this method variation of parameters, we found these expressions based on the fact that y double prime had a coefficient without any variable. So we did this based on the form of the equation y double prime plus p y prime plus q y equal to 0, right? So that means we didn't have anything multiplying the y double prime. So to do this, to get the correct uh, forcing function g of x that is going to get input into u1 and u2, we need to divide both sides by x to the power that multiplies let me do this again, that multiplies, so x squared, the y double prime term. So that's going to give us the following g of x, that is 4x ln x over x squared, that is x over x squared, that is 4 ln x divided by x. So that is going to be really our g of x. So be careful. It's not going to be exactly as it shows in the original equation. So here we go. Let's set up the integral, that is the integral of negative y sub 2. Be careful, negative y sub 2 is x to the negative 1, so that'll be negative x to the negative 1 times g of x, which is 4 ln x over x, then divided by the Wronskian, which is negative 2 x to the negative 1, and let that be with respect x. Okay, so number one, this is what we're going to do. Number one, x to the negative 1 cancels with x to the negative 1. Also, negative over negative equals to positive, and 4 divided by 2 equals to 2. And I'm going to take that 2 outside of the integral, and that's going to leave us with simply ln x over x with respect x. Okay. All right, well, so this integral can be evaluated using a u substitution, because u equals to ln of x, and du, which is 1 over x dx, it's there in the integrand. So this is simply, let me write it in the next line right here, that is 2 times the integral of u du, which is the integral of 2u, which is u squared. And of course, I'm not going to write the plus c, because we're only in the middle of an intermediate step. All right, so that's simply back substituting. That's ln of x quantity squared. All right. Okay, so that's our u1. What about our u2? u2 will be the integral of y1 g of x divided by w with respect x, where y1, what's y1? Isn't that just x? Okay, that's the integral of x. The forcing function, again, it's the same. Okay, let me do this. 4 ln x over x, and divide by negative 2 x to the negative 1. All right, there's a couple of calculations we could do. Number one, or rather simplifications. So number 2, we could divide out this x with that x. Also, 4 divided by 2 equals to 2, and positive over negative is negative. So this will be negative 2 times the integral of, actually, this x to the negative 1 in the denominator can be moved to the numerator with positive 1 exponent. We don't need to write the 1. It's invisible. It's there. And multiply with ln of x dx. All right. Well, so actually, to evaluate this integral, we would need integration by parts. And to make this video a little shorter, so I'm going to skip the steps to the integration by parts. I'm just going to give you the result. So this would be careful, because we have a negative 2 coefficient. So that is negative 2 times whatever we get from integrating this one by parts, which is x squared over 2 ln x minus the quantity x squared over 4. All right, which is, well, let's simplify this by distributing the negative 2 that it's multiplying outside. So negative 2, the 2's cancel right here, leaving us with negative x squared ln x, and the negative 2 over times negative x squared over 4, that leaves us with positive x squared over 2. All right. Okay, so these are u1 and u2. Again, back when we were solving differential equations using the method of variation of parameters, the form of y sub p would be a combination of u1, y1, plus u2, y2, where u1 and u2 are the results we just found using the integrals, and y1 and y2 are the solutions to the the linearly independent solutions to the related homogeneous equation. Okay, so that is u1, which is ln x quantity squared, times y1, which is x, plus all this negative x squared ln x, okay, negative x squared ln x, plus x squared over 2 times u2, y2, which is x to the negative 1. So this is going to look a little big. Well, let's actually do some simplification. So number 1, y sub p equals to, on the one hand, ln of x quantity squared times x remains the same. Actually, I'm going to write that x in the very front. Looks better. And I'm going to distribute x to the negative 1 right here and multiply with negative x squared. That's going to leave us with negative x ln x, and over here distributing with the other x squared over 2, that's going to be plus x over 2, or 1/2 x, either way. So that is the most simplified version of the particular solution part. All right, now let's write the general solution, which is a combination of y homogeneous, or y sub c, plus y particular, which is y sub c, what was that? C1 x plus c2 x to the negative 1 plus y sub p, which is x ln x quantity squared minus x ln x plus 1/2. I'm going to write it as 1/2 x because there's something I would like you to see better. Okay, we did one, or rather, we were in a situation similar to the one we're just going to get here when we were doing variation of parameters. See how c1x, 1/2 x, those are essentially like terms. And again, by absorption, I'm just going to write c1x to take into account the addition of c1 plus 1/2. It doesn't matter what that new constant is, it's just a constant. So really the general solution will be y equals c1 x plus c2 x to the negative 1 plus x ln x quantity squared minus x ln of x. Final answer, right? So that's final answer to the solution to a non-homogeneous differential equation in the Cauchy-Euler form. And to wrap up the section, what about higher order Cauchy-Euler's equation? So although it's possible to come up with auxiliary equations for higher orders, what we're going to do in this case is simply because, well, we don't know what the characteristic cubic equation would be, or auxiliary cubic equation be. I mean, we can deduct it in a similar way as we did it over here at the beginning of the section with a generic cubic equation, but actually we will do it by brute force, so to speak, you know. So, well, the approach would be by finding the consecutive derivatives, that is y prime, which is again mx to the n minus 1, y double prime, that is m times n minus 1, x to the m minus 2, and y triple prime, that equals m times m minus 1 times m minus 2, x to the m minus 3. All right? Okay, so let's substitute these three derivatives into this third order differential equation. I know this one is going to be kind of a long one, but you will see how that will work anyway. All right, so x cubed times y triple prime, which is m times m minus 1 times m minus 2, x to the m minus 3. Okay? Well, actually, guys, to save some time, how about we write this x to the m minus 3 already as x to the m times x to the 3. All right, I'm going to do the same with the second order derivative and the first order derivative. All right, and then plus 2x squared times y double prime, which is m times m minus 1 times x to the m minus 2, but I'm going to write the x to the m minus 2 as x to the m times x to the second, or x squared, and then plus x times times y prime, which is m x to the m minus 1, which is the same as saying again x to the, actually this is x minus 2, and this is x minus 3, and this is x minus 1. All right, so that is times, no, that's about it, right? Okay, so minus y, which is simply x to the m, and let that be equal to 0. All right, so the reason why I wrote as this x to the m minus 2, x to the m minus 1, and x to the m minus 3 as products is so we can cancel these two, cancel those two, and cancel x with x to the negative 1. All right, well, let's see what we are left with. So we are left with the quantity m times m minus 1 times m minus 2 x to the m plus 2m times m minus 1 x to the m plus m x to the m minus x to the m. Let that be equal to 0. Notice again, in a similar way as the deduction of the auxiliary equation for the second order differential equation, x to the m, it's a common factor. Let's factor it out, x to the m, and this will be m. And how about, well, after factoring again to save some time, I'm going to expand this binomial. I'm going to leave this m at the end, so that'll be m squared minus 2m minus m plus 2. And then I'm going to distribute the 2m over here. That's 2m squared minus 2m, and simply m plus m, and then minus 1, because we factor x to the m. And let that be equal to 0. All right. Well, so this negative 2m minus m will be negative 3m, and I'm going to distribute the m over the three terms right here. I don't want to write the entire equation. I think you can easily see what's going on here. Okay, so that is x to the m times m cubed, m times the negative 3m, that is minus 3m squared, and then m times 2, that's plus 2m, and then plus 2m squared minus 2m plus m minus 1. All right, and let that be equal to 0. Okay, so let's combine like terms right here, x to the m, and well, that's going to be m cubed, and then let's combine the quadratic terms, minus 3m squared plus 2m squared, that's minus m squared. The linear terms, that is 2m minus 2m, cancel out, surviving 1m right here, so plus m, and then minus 1, and let that be equal to 0. Again, at the beginning of the section, we discussed that the x to the m factor is really not relevant. Actually, we would go with the polynomial m cubed minus m squared plus m minus 1. I mean, not that it's not relevant. I mean, it's part of solution because that outputs the solution, the trivial solution, y equals to 0, which is not a very interesting function. All right, well, so let's solve this equation. Actually, I mean, you can use the rational root theorem, but actually we can factor by grouping right here. That is, factor m squared in the first group. That's going to leave us with m minus 1 plus, did you see this m minus 1 right here? All right, that equals 0. There is an invisible 1 right there that we could write to make it look like as if we factor something out. Well, the new greatest common factor, which is m minus 1, that is times m squared plus 1. And let that be equal to 0. So using the zero product property, again, m equals to 1 and m squared equals to negative 1. That is m equals plus or minus the square root of negative 1, which is plus or minus I, which again I'd rather write it like 0 plus or minus I. Alright, so in this case we have two cases in the same solution. Number one, we have a real solution, which would be y equals to c1 x to the m, okay? In this case, let me call this m1, right? Plus x to the alpha c2 cosine of beta ln x plus c3 sine ln x. Oh wait, beta ln x. Make some room right here. Okay, there we go. So this will be okay, let's just substitute the numbers. Y equals c1 x to the m sub 1, which is x to the first power, plus x to the alpha, which is x to the 0 power, c2 cosine of beta, which is 1 times ln x, plus c3 sine beta, which is 1 times ln x. Okay, and well, let me just simplify or clean up these ones and zeros that are not necessary. So this is c1 x to the first, which is just x. X to the 0 is simply x to the 0 is just 1 times all this madness here, c2 cosine 1 times ln x, that's simply ln x, plus c3 sine 1 times ln x, which again is ln x. And that is our final answer to the third order equation. Alright guys, well, of course, I mean, what if we were to solve a fourth order differential equation, a fifth order differential equation, or maybe another third order differential equation? It might be tedious to keep doing all the substitution of the derivatives of all subsequent derivatives of x to the m. Well, let me just write down the generic third order differential equation, that is a x cubed y triple prime rather plus b x squared y double prime plus c x y prime plus dy equals to 0. So if you substitute these derivatives in a similar way we did over here, these three derivatives, I mean y and the three derivatives, you should get the following auxiliary or characteristic equation. That would be a m cubed plus b minus 3a m squared plus quantity 2a minus b plus c m plus d equal to 0. So you would substitute, you would identify the coefficients a, b, c, and d, substitute into the auxiliary equation, and then solve that cubic equation, maybe by the rational root theorem, maybe by factoring, or whatever works best for the solution to that polynomial equation. I mean, I'm not going to do all the process to get into this solution right here, into this form. However, it would follow similar to what we did at the beginning of the section here. Essentially, this process to obtain the auxiliary or characteristic equation for the second order differential equation. All right, again, I'm not going to do it. If you want to do it on your own, if you're curious about it, I encourage you to do it, but this is just just an extra piece of information. Also, I mean, this equation can be found if you Google it up. You could also find auxiliary equations or characteristic equations for fourth order, fifth order. Just Google them up, and I'm pretty sure you should be able to find those results. For now, that's it for the day. So that's it for the video for Cauchy-Euler's equations.